Hello friends, welcome to the whiteboard tutorials, and today we are going to talk about mother of basics in electrophysiology. By mother of basics I mean that the most conceptual part of electrophysiology we'll be dealing it with today. Now before going to the conceptual part of electrophysiology, just to give you a quick introduction here of electrophysiology, we are going to deal about the concepts of membrane potential, that is membrane physiology, how it attains the resting membrane potential, that is the conceptual part of the resting membrane potential, which we usually overlook in our studies, and those doubts I'm taking this topic. Now what do I mean by mother of basics? Now here as we study, we generally overlook one most important concept in electrophysiology, and I guess you know it. Now the topic that we usually skip is Nernst potential. Nernst potential. In this video I will focus my all diversion in this. I will divert into this topic only. Now the Nernst potential topic is so important that all the dynamicity of membrane is dependent on this topic, and we generally skip this because we don't understand this. As being the most important, we need to get it very clear to understand all the further points which lays the concepts of every physiological studies. Now just to give you a overview of Nernst potential, we are taking a polarized cellular membrane of nerve tissue, nerve membrane. Now here we have cell membrane, and we have, as I said, we are taking a polarized membrane. We know in polarized membrane the outer interface of membrane maintains a positive charge, and inner interface of membrane, that is inner side of membrane, maintains negative charge. And about this we might also ask about what happens inside the cell. Actually all the positive negative ions are distributed specially randomly, so they cancel out and creates a net zero charge. So we overlook this system, we only pay attention to here. Now and this region only conducts the action potential further. Now as we see that, as we always see in every diagram of physiology book, that it is made on the diagram, and we assume it that it is a definitive state, and we don't try to actually analyze it, that how did it reach, that is resting membrane potential. Now as we know, there are ionic channels, membrane or integral proteins which maintain this, but prior to that also a more important concept plays a role. Now today we are going to study that only. Now the focus of study would be this part, and I am now taking an example ion by ion, that is I am taking example of sodium ions. As we know, it is ECF, it is intercellular fluid, and in ECF we know that sodium ion concentration is more than ICF, that is intracellular fluid. Now taking an example of sodium ions, now as we are focusing our study only on individual ion, that is sodium ion, although there are many other ions also, that potassium ion, chloride ions, and other ion also which plays a role. But to understand this topic, we are taking this example of sodium. As we know, for example, we take example of sodium sodium cations. So the concentration is here more, and here we have comparatively less. Also there are negative charges distributed both outside the cell membrane also, inside the cell membrane also. They are composed of chloride anions, protein and negative proteins which have a net negative charge. So we have a distribution of negative charge also here also. Now we will go by a natural most physical concepts now which we can see. Now first of all we can see the concept 1 that drives the, for example, when we have an action potential in initial stage, we have an inward flux of sodium ions inside the membrane. Now why is that so? Because it's due to diffusion, due to concentration gradient. Now first point is concentration gradient is playing a role in dynamicity of cell membrane, as we are studying about dynamicity of cell membrane and the main concept which maintains the polarized state of the cell membrane. First point is the concentration gradient. Now when the sodium ion influx takes place, we know after a short period of time it gets prevented, that it gets blocked, and it doesn't continues forever, that the inward flux of ion is usually blocked after a certain time. Now why it happens so, and it is very important to know. Now as we realize that sodium ion is coming inside the cell, so we can expect in this region we can expect that a certain amount of sodium ion takes place, concentration of sodium ion they resides here, and the electropositivity is maintained. By electropositivity I mean the charge of ion is positive and therefore it gives an electric field around it, that is electropositive field. Now here as sodium is moving here, so the net negative charge would become more in concentration, as from here some many sodium ions are influxed into cell membrane, so it will give a net electronegativity. Now as we suppose that there was a concentration gradient here denoted by green, that is concentration gradient. Now we are slowly and gradual, actually it's not a gradual process, it's a very fast process. But very fast process, the gradient, one other gradient also plays a role here. As we know, the concentration gradient was playing a role in first stage. Now in second stage a second gradient plays a role, which is very important to note and which we often skip this, that is electrical gradient. Now what do I mean electrical gradient? Now just to tell you, the electrical gradient is just opposite to the concentration gradient, therefore it cancels the further influx of sodium ions. Now we have now reached up to this point where the electric gradient is preventing the further influx. Now why it happens so? What is the basic concept in this? Just to tell you this, that here I will tell you how the electrical gradient comes into play and how it prevents the further influx of sodium ions. Now here is the final situation of the combination of gradient. Here were sodium ions more, and here were negative chloride ion or any anionic proteins. Now I am representing this situation as this. Assume it a positivity here and negativity here, electronegativity and electropositivity. Now as we know, the positive and the like charges repel each other and the negative charges also repel each other, that is the like charges repel and unlike charges attract. Now here, as a potential is built up here, so more that the charges which are left there, as always they are, as we can say that all the sodium ion in the actual fluid in this ECF has not been reached here, because due to this, as the more the charges which are trying to move inside into the cellular membrane due to concentration gradient are repelled by this electropositive charge, which prevents the further influx of the sodium ions, and this actually prevents the further influx of sodium ions to stabilize the condition in net polarized stage, which is a very important, crucial part of membrane physiology and is the most basic concept of electrophysiology. I would like to stress this point again. The sodium ion which were built, the electropositivity which was built due to sodium ions repels the coming sodium ion charges from outside, which is called the Nernst potential, and this potential is what we call as a Nernst potential, as it is the diffusion potential. It is that diffusion potential which is built here, that as we potential we mean it is at higher stage, higher potential, and it is a negative potential. As we have you can assume it as a battery which maintains a certain voltage which prevents the positive charges coming from here. As you can see, the negative charges can't move, and the positive charge, as we said that negative charges are relatively stable than the positive ions. Now, the sodium ion would not be able to move inside due to the repulsion of this electropositivity, and this plays a key role in the electrophysiological aspect of membrane. Now, this was the most important concept of the electrophysiology, and I hope that this is now clear in your minds. And so we can define the Nernst potential as, in more simpler language, we can define it as Nernst potential. It is the potential gradient which blocks or prevents further influx of positive ions. That, as I took the example of sodium ions, it may be the case of potassium ions or any other ions. Now, in real physiological situation, how it takes place? As we know, there are many ions. For example, I am taking this as cations and these are anions. Now, each Nernst potential plays a key role, and all the summation of that Nernst potential decides the diffusion potential of the membrane. It is not that only sodium ion is taken into account. All the cations are here and here have a certain value of Nernst potential, which finally decides the diffusion potential of cell membrane, of the dynamic cell membrane, and which is very important to note. As in action potential, we have a crucial concentration gradient of the ions to conduct it in a forward or any direction.